Hello viewers, today I will be talking about the topic which is so very important that you cannot avoid studying that topic if you are appearing for any chemistry exam in any competitive exam, uh, maybe it IIT JAM, GATE, CSIR NET, or the traditional undergrad and postgrad chemistry honor students and their exams as well. So today I will talk about photochemistry, and here in this lecture I'll be talking about the full course of photochemistry, and in one shot I will complete the course including discussing problems and their solutions. So this will be a overall discussion about the photochemistry in terms of the theories, the reactions, and the problem and solutions, everything. So before I move further, so next I will be talking about the basics of photochemistry. And before I move further regarding this thing, allow me to tell that the study of the chemical reactions or isomerizations and physical behavior that may occur under the influence of visible light or ultraviolet light is known as photochemistry. Okay, so this photochemistry and eventually the chemical reactions are initiated by light are known to us as photochemical reactions. So this photochemistry or photochemical reactions are guided by two fundamental principles, which are the foundation for understanding the photochemical transformation. The first one is the first law of photochemistry, which is rather known as the Grotthuss-Draper law, which states that the light must be absorbed by a chemical compound or a chemical substance in order for a photochemical reaction to take place. That is, this is the first step or mandatory step that the molecule need to absorb light. Okay, and the second law of photochemistry, which is generally known as the Stark-Einstein law, and it says that for each photon of light which will be absorbed by the chemical system or the substance, whatever we name it, only one molecule is activated for subsequent reaction. Okay, so this photoequivalence law was first derived by Einstein during the development of the quantum theory of light. So this is, you can imagine how important this is. So therefore in photochemical reactions it has to be initiated by light, and the energy absorbed or emitted by matter in the discrete quanta is called the photons, and their energy is calculated with the famous equation E equal to h nu, or eventually E equal to hc by lambda. So here lambda becomes quite important as wavelength becomes significant with the short wavelength leads or correspond to higher energy. For example, if you irradiate the molecule with 350 nanometer wavelength of light, and it will correlate with energy amounting around 343 kilojoule per mole. So you can understand the correlation between the lambda and the energy from these parameters. Now first, before I go into these the last 3 points over here, so far you can see on the slide, the first question that comes on our mind is what happens when light is absorbed by a molecule, right? So when the irradiation takes place, the electronic configuration changes of the molecular energy levels of that molecule. Now the Frank-Condon principle says that the heavy atom nuclei do not change their positions. Okay, now this leads to an initial geometry of the excited state, which is usually not the energy minima. Okay, so during this excitation the electron spin remains unchanged, and the spin inversion during excitation is forbidden, as we know from the quantum mechanics, and therefore it is unlikely to happen. Now right after the excitation several things can happen, and I will talk about that into the next slide as well. But before I go there, I would like to say with some minimal emphasis on them that there are several things can happen. For example, so far maybe 5 things I think. And first, the vibronic relaxation can bring the molecule quickly into the new energy minimum for the excited state, of course, because it has irradiated by the light, and the energy is released into the solvent as a result. Second option is the intersystem crossing can take place, and it will lead eventually to triplet states, and this will accompany the spin inversion, the intersystem crossing from the singlet to triplet. This can happen as well. And in the new energy minima is reached by the vibrational relaxation, of course. Third point can happen that the emission of light and the return to the ground state will lead to several phenomena like luminescence, fluorescence, phosphorescence, etc. Quenching can also happen, and at the excited state, of course, and the energy is transferred to another molecule. And usually we observe diffusion control dynamic quenching by collision. So it is a collisional phenomena. And the last possible thing is the radiation-less deactivations or decay, where the molecule goes back to the ground state by the vibrational deactivation, and no light emission takes place during that part, and the energy goes to the solvent or the environment of the molecule. So the absorption of light first will lead to an electronic excitation. Most of the molecules tend to be at the ground state. So from ground state, they will move to the excited state, and it will promote an electronic transition in the energy levels within the molecule, like from non-bonding to the antibonding pi orbital, or from the pi orbital to the antibonding pi star orbital. And in the excited states, singlet and triplet, like S1 and T1, are the most favorable positions or the energy levels where from the reactions are generally take place. Okay, so before I move into further, I just want to share the S1 and T1 in terms of their half-life time. As you can see over here, that S1 have a shorter half-life time and higher energy, of course, where the half-life time is associated with 10 to the power minus 9 to 10 to the power minus 5 second. And for T1, this is less in energy content compared to S1, and it has a longer lifetime of 10 to the power minus 5 to 10 to the power minus 3 second. Okay, so this is in terms of T1 and S1 in terms of their half-life time. Next, I will be talking about Jablonski diagram. This is the best representation where the excited states and the associated phenomena, how they take place, and the best possible way we can understand that. So this is the graphical representation you can see on the screen, and at S1 and T1, different things can happen. I have written over here. I first read out those things, and next I will be discussing about the diagram. At S1, 4 things can occur: radiation-less decay, the molecules can undergo chemical reactions, or the molecules can undergo intersystem crossing, and fluorescence can take place. At T1, 3 things can occur: radiation-less decay, the molecules can undergo chemical reactions, and phosphorescence. Okay, so these are the possible fate of molecules at S1 and T1. Now coming into the Jablonski diagram, you can see that most of the molecules are preferred to be at the ground state level and the singlet state, most of the molecules, of course, and having several vibrational energy level at each singlet and triplet state, be it in the ground state or excited state. When the irradiation takes place on the molecule which are supposed to be at the ground state singlet, the molecules get excited and move to the excited singlet states, where each state is also subdivided into several, or consists of several vibrational energy states. Now from here, few things can happen. First is the internal conversion, which is the energy dissociation or the conversion. For example, the distinction between the singlet and the triplet state is important here, because the photon induced always lead to the state of same multiplicity. That is, it can go to the singlet to singlet or triplet to triplet. And since most ground state are singlet, this phenomena or that the excited state initially formed by absorption of light must be the singlets. Okay, now the internal conversion of excited states of lower energy states of the same multiplicity takes place rapidly with the loss of heat energy, or we can say the relaxation process. Alternatively, an excited state may return to the ground state by emitting a photon via the radiative decay, and in case of, and that will eventually lead to the fluorescence, and in the other case, the conversion of singlet state to a lower energy triplet state, or the vice versa, this is also possible, is known as the intersystem crossing, and this is a slower process than the internal conversion. And radiative decay from the triplet state is known as phosphorescence, and all these are marked with different colors, the words, so it will be easier for you to understand that. Along with that thing, quenching is also another phenomena which is possible when the molecules can transfer the energy to another molecule and come back to the ground state singlet level. Maybe a quick recap of whatever I said in last few minutes, that if a molecule absorbs energy, it can undergo a reaction or it can undergo the loss of energy by two methods. First one is the radiative process, which involves the emission of a photon, which again possible in further two ways. First is phosphorescence, which involves the relaxation of a lower state with a different multiplicity, such as the electronic transition is from triplet 1 state to singlet 0 state, which is spin forbidden. The second process can be the fluorescence, which is the relaxation to lower state with same multiplicity, such as from S1 level to S0 level, and this is eventually spin allowed transition. The second process which can be associated with the phenomena of photochemical irradiation will be the non-radiative process, and that will involve no emission, and this includes the internal conversion, which involves no spin change, such as from S1 to S0, and the intersystem crossing, which involves the change in spin multiplicity, and one way competes with the phosphorescent decay of the lowest triplet state to the ground state. Another way converts the lowest excited singlet state to the lowest triplet state and competes with the fluorescence and internal crossing. Okay, and the external by energy transfer to some other molecule is sensitization, and the deactivation is known as quenching. I hope so far the process of photochemistry and associated reactions of photochemical irradiation are quite clear to you. So now I will be moving to the alkene isomerism or the geometrical isomerisms in alkene. Those are important phenomena, and for the formation of the lowest excited singlet state of simple alkenes, the phenomena arises from the allowed pi to pi star transition for them. Now here, as you can see, a trans olefin upon photochemical irradiation converted into the cis one and in equilibrium with that one. Now in case of cis trans, or we can name it EZ, isomerism under photochemical conditions commonly leads to the thermodynamically less stable cis isomer, and this cis isomer typically absorbs at a lower delta value due to decreased conjugation because of non-bonded interactions. Now, third point is the reactions come to photostationary state unless optical pumping is performed, which is the irradiation of just one isomer to drive the equilibrium. Now, the example of cis and trans stilbene is quite known and is of first kind, rather to say, and in that case, for the different absorption spectra of the Z isomer can be enriched in the photostationary state, as you can see over here, that without the sensitizer at the photostationary state, the Z isomer predominates at, and as the ratio of EZ is around 8:92. And with sensitizer, the photostationary state, at the photostationary state, the ratio becomes 50-50. Okay, so this is the general phenomena that has been associated with the geometrical isomerism of the alkenes. Now, just I would like to say that that absorption of solvents and lack of suitable light sources sometimes makes it difficult for the simple alkenes to participate in the photochemical reactions, and that can be overcome by the substituted or conjugated derivatives of the alkene if we use that as in the photochemical reactions actually. And there is another possibility to circumvent the problem of absorption at short wavelengths is the use of sensitizers. As you can see here, in case of trans-stilbene and cis-stilbene, you can see here that with the help of sensitizer at photostationary state, we resolve the we get the easy mixture at 1:1 mixture, or 50-50, whatever you say. Eventually that will lead to 1:1 mixture. So next I will be talking about some examples, because the geometrical isomerism of alkene and their participation in photochemical reaction is quite well studied, and I will share some examples with you. So first one, you can see this trans olefin. So this having 5% in yield, and eventually that goes on photochemical irradiation in the forward direction to yield the cis isomer. Similarly, with the trans isomer, it can move to the cis isomer as well. For the second example, as you can see here a little bit different in terms of the cis trans isomerism. Now here from the cis one, it goes for the trans isomerism. And here as well for the beta ion, you can see if the reaction vessel is made up of quartz, so the delta the wavelength of the light would be more than 180 nanometer, of course. And this beta ion on photochemical irradiation will again isomerize. The isomerization takes place to the cis one, and the cis isomer eventually upon 6-pi electrocyclic ring closure will lead to alpha pyran derivative. So this is the geometrical isomerism in leading to another ring cyclized product by means of photochemical irradiation. Next, there are also examples. You can see, you can go through that thing. These are common examples, well studied olefin isomerization process. Here also you can see this is a ring structure, and along with a alkene chain is associated with that ring structure, cycloheptanone basic skeleton upon photochemical irradiation using uranium glass, and so the wavelength value should be more than 340 nanometer of range, and eventually that will lead to a mixture of isomers having the fused ring structures. Another example with furan as the substitution or branched chain, and that will lead to the mixture of heterocycle fused ring structures, of course. And here the glass vessel used in the Pyrex, so the wavelength will be associated with more than 285 of. Next, I will be talking about electrocyclization reactions. In organic chemistry, an electrocyclic reaction is a specific type of pericyclic rearrangement where the net result is one pi bond being converted into one sigma bond, or the vice versa. Either way it can happen. And usually they are categorized by following criterias or characterizations, and that involves, like here you can see that the reactions generate a new sigma bond between the termini of the conjugated pi system, and it's been a concerted process. That means the bond breaking and the bond formation or making occur simultaneously at the same time, and the reactions also come to photostationary state based on absorption coefficient at the lambda of irradiation, that is the wavelength of irradiation. And in this kind of reactions, either the ring opening or ring closing can take place, and Depending on the type of the reaction, it can happen through either a conrotatory mode or a disrotatory mode. If you have already gone through the pericyclic reactions, these terms are quite known to you. And also the type of the rotation determines whether the cis or the trans isomer will be in major during the product formation. Okay, so here first I will give a small presentation regarding the thermal and the counter photochemical reactions, where in thermal reactions we know that the 4n pi system goes with a conrotatory mode of ring closure, and for 4n plus 2 it goes with a disrotatory mode of ring closure or opening. In case of photochemical reaction, this is the other way around. Here the 4n pi system adopts the disrotatory mode of ring closure or ring opening, and for 4n plus 2 pi system it adopts the conrotatory mode of the ring opening or ring contraction. Next, I will be sharing some 4 pi electrocyclization reactions and their examples, as you can see over here. The first one being the cis-diene in equilibrium after photochemical irradiation into after the electrocyclization process, and you see the product. Similarly, the second and third cases, these are similar kind of reactions, and usually for the definitively the 4 pi electrocyclization occur with the disrotatory ring closure under the photochemical condition. In second example, you can see a new ring has been formed. So the 6-4 fused ring has been formed and a new pi bond has been formed, as you can see in the reaction with 95% presence of the ring cyclized product. Third example shows the cyclohepta dienone, which upon photo irradiation, again it goes upon electrocyclization process and a ring closure, providing a fused 4-5 fusion ring, the carbonyl compound in 59% of yield. In case of pyran 2-one, upon photo irradiation, we see that it can adopt a chair-like transition after the electrocyclic ring closure of the 4 pi systems, and upon decarboxylation and reaction with pentacarbonyl iron under the photochemical reaction, of course, it can coordinate the cyclobutene ring, can coordinate with this iron carbonyl compounds and form organometallic compounds. For 6 pi and 8 pi electrocyclization reactions, the 6 pi systems undergo the conrotatory ring closure, as I have said earlier, whereas the 8 pi electrocyclization prefers the disrotatory ring closure under the photochemical reaction conditions. You see the example on the right hand side on the screen. There is another example given here, the provitamin D, which upon photochemical irradiation will be converted into the pre-vitamin D, which is known as precalciferol, and you see the ring opening takes place over here. Okay, and this on further 1,7 hydrogen shift at higher temperature above 20 degrees centigrade converted into the calciferol, which is known as vitamin D2. So these are reactions where the 6 pi electrocyclization process takes part and further followed by 1,7 hydrogen shift. Eventually from ergosterol we get the calciferol, that is vitamin D2. So these are examples of 6 pi and 8 pi ring systems. Next, I will be talking about the photochemistry of carbonyl compounds. This is a very rich chemistry of carbonyl compounds photochemistry, and it has quite a variety, of course. And the carbonyl group has the sigma bond, pi bond, and the non-bonding electrons. We know that. And when the energy is supplied, that is the photoirradiation takes place on a molecule having the carbonyl compound, it supplied the electron, and the electron transferred from the non-bonding level to the antibonding pi star, and also from the pi to the pi star level. Okay, so these are two transitions that are associated with the carbonyl compounds photochemical reactions. Now, for the carbonyl compounds, when N to pi star transition happen, the reaction occur in singlet or triplet state. Okay, but in case of pi to pi star transition for sensitized reaction conditions, the reaction occur only in singlet state. Okay, so this need to be memorized. Now, the most important and highlighted part or the name reaction of this carbonyl groups photochemical reaction is Nourish type reactions. And these are two types, Nourish type 1 and Nourish type 2. And so I'll come first with the Nourish type 1, which is actually the alpha cleavage of the carbonyl compounds. And this homolysis of the aldehydes and ketones into two free radical intermediates, that is the alpha scission, takes place in case of Nourish type 1 reaction. Okay, the carbonyl group accepts a photon and is excited to a photochemical singlet, and through intersystem crossing the triplet state can be obtained from the singlet one. Okay, and now on cleavage of the alpha carbon bond from either state, the two radical fragments can be obtained, and the size of and the nature of these fragments depends fully upon the stability of the generated radicals. So the radical stability is an important factor. Another thing what I would like to say for Nourish type reactions, for carbonyls, to proceed via the Nourish type reaction, it prefers the vapor phase condition. Okay, so in vapor phase, the decarbonylation takes place and it facilitates the reaction to proceed further. And what we need to take into our mind, that we need to check for the radical stability. Okay, so here first example, the alpha dimethyl cyclohexanone upon photo irradiation or in presence of photon, it will, the alpha bond, the alpha scission will take place, the alpha cleavage of the carbonyl group next to carbonyl group, that alpha bond that will cleave, and we will get more stable radicals, as you can see in the third bracket. Okay, so this biradical will have three fates. It can either from the alpha position of the carbonyl radical, it can abstract hydrogen from there, and if it does so, it lead to ketene, or the other radical at the other terminal at the carbon radical, other carbon radical can abstract hydrogen from the adjacent carbon centers from the methyl groups. If it does so, we will get a terminal olefin. If it abstract hydrogen from the other alpha carbon, so it will lead to more substituted double bond. So these are three possible products from the more stable radical, as you can see over here. Other examples are here also, where the cyclopentenone can cleave or can yield the butadiene system upon decarbonylation process. You can see a carbon monoxide molecule is the product as well. Similarly, in the second example also, when the cyclopropane fused cyclopentenone upon photoirradiation produce a dipymethane kind of substrate, and also decarbonylation proceeds in that case. The third example, or the fourth example rather say here, with the cycloheptanone upon photoirradiation, it can have two fates, as I said before, that in absence of sensitizer, the transition will lead, or the excited molecule will go up to the singlet state, the N2 pi star transition, and from there on it can, in the electrocyclization process or in the Nourish type reaction, it will eventually lead to the decarbonylation and produce the acyclic triene. Okay, so this acyclic triene is the product, and decarbonylation takes place. In presence of sensitizer, the reaction goes in a different pathway, and the molecules, the N2 pi star transition takes place, and the molecule goes into the excited triplet state. And thereon, the electrocyclic ring closure takes place, and we get a 4,5 fused ring as the major product. So we will see a couple of more examples on this Nourish type 1 reaction. Here you go, with the monomethyl substituted at the alpha position of the cyclohexanone compound. It can have two different pathways, or two different alpha bond can be cleaved. One is the carbonyl carbon, which is attached with the carbon having the methyl group, that one, and the other side, the another one. So both the biradicals formed here, you can see after the immediate photo irradiation from the starting substrate, this can have two different routes of producing products. With the usual alpha scission, that is the bond, the CC bond having the carbonyl group and the methyl substituent, when that cleaves, that yields with a product with the trans isomer which is thermodynamically stable and yielding that in 75% as measure, compared to the cis isomer which the olefin which is formed in 25% yield. Coming to the other way around, when we are talking about the other radical which is comparatively less stable because the terminal radical is a primary carbon radical, so it will lead to the terminal olefin containing the carbonyl group, of course, in the structure. So this will be the trace product. Because the radical stability was very important, as I mentioned, so this will lead to the product which is in the trace formation. Okay. Next, we will talk about another example. As you can see here, this is the bicyclopropane cyclohexanone compound. So upon alpha cleavage on photoirradiation, the cyclopropanyl radical will be generated, which is the usual route or expected one, and then first ring opening can take place, producing the olefin, and the acyl radical or the carbonyl radical, of course, still present in the molecule, and then the cyclization can take place with a 9-member ring having still a flanked cyclopropane ring. So that can further goes for the ring opening, and further cyclization process will lead up to the final product with an you can see the carbonyl compound. So these are reactions which are very important examples of Nourish type 1, and these are very important for the exams if you appear, for example, IIT JAM or CSIR NET. So those examples are very, very important. Next, I will be talking about the second type, that is Nourish type 2 reaction, where the Nourish type 2 reaction is actually the photochemical intramolecular abstraction of a gamma hydrogen by the excited carbonyl compound, and that eventually produce 1,4 biradical as the primary photoproduct. Okay, so this can further be converted into the desired products or the undesired products in some cases. So there are variety of product formation in case of Nourish type 2 reactions. The secondary reactions that can occur are the fragmentations, that is the beta scission to form the alkene or enol, which rapidly can tautomerize to the carbonyl compound again, as you can see in the mechanism here or in the reaction scheme, or the intramolecular recombination of the two radicals to a substituted cyclobutane ring is also product for some cases. So if I take a highlighter and if you see the gamma hydrogen over here, this one will eventually be abstracted upon radical formation, and you see the hydrogen, the O dot can abstract that one, and we can have the carbon radical which is more stable 2-degree carbon radical here, and also here another carbon radical which is the 3-degree carbon radical. So these are 1,4 biradical systems, and in the singlet state, of course, and this can eventually go for the intermolecular cyclization, that is recombination of these radicals will lead up to the cyclobutane ring and the OH group, of course, there. And for the Nourish type reactions, this singlet state can eventually goes, so this is the Nourish type product. In that case, it eventually goes for the excitation to the triplet state, and from there the spin conversion takes place, the intersystem crossing takes place, and from there it can yield the racemic 5-methyl-2-heptanone as the major product from this biradical singlet state biradical compound. I hope you understand that part. There is another example, the cyclopropyl carbonyl compound, another one. Upon HNU or the photoirradiation will end up with alpha beta unsaturated carbonyl compound like this. So we will have a couple of more examples, 3 to be exact, on Nourish type reactions, and in my next class or next session when I will be talking about the problems and their solutions on this photochemistry or photochemical reactions, so I'll bring up more examples and more solutions to the problems for this kind of reactions. So here you can also see that the gamma hydrogen over here, if I can take the highlighter, the gamma hydrogen here, this need to be highlighted, and this abstracted upon the generation of the radical, and followed by as I said, that one route can be the intermolecular way or the recombination of the biradicals to form the cyclobutane ring. The other way leads up to the enol and alkene, as I said, and the enol eventually tautomerizes to form the carbonyl group. Here, if the R group is alkyl, eventually that will be a ketone. Next example is that one. So this is a carbonyl compound having a gamma hydrogen, as you can see, and let me take the highlight. Yeah, as you can see, the gamma hydrogen here, and also a tertiary butyl group attached with the carbonyl compound. Now, if it after photoirradiation, the molecule get excited and it goes to the singlet state, and from there on it can have the fate of, as I said a little bit ago, that it can form the intramolecular cyclization and the recombination of the 1,4 diradicals or biradicals to form the cyclobutane ring, along with the carbonyl compound, which is eventually generated from the enol and the olefin. So this is one fate. And if it goes with the triplet state in presence of sensitizer, then the tertiary butyl radical can be generated along with the carbonyl radical and still having the gamma hydrogen intact. From there on, it can lead from the tertiary butyl radical can lead to the formation of isobutane, and also from the other carbonyl radical it can form the carbonyl compound, the olefin, and some other byproducts as well. So these are the fate of as I said, that in Nourish type reaction several other byproducts or side reaction can proceed or facilitates. So these are example of that one. And the next example is, as you can see here, the bicyclic ring system having a carbonyl substituent attached with the bicyclic ring system. So this is basically a bicycloheptane 2-phenyl methanone, that compound, and upon photoirradiation it will abstract the gamma hydrogen. The carbonyl radical will abstract the gamma hydrogen within the molecule, and if I can see that it will be abstracted from here, from this carbon, and you can see here the radical will be generated at that part. Okay, and an oxygen radical will be there at the part of the carbonyl compound. So that these radical counterpart or the radical intermediates eventually lead to the product formation, which is the cyclopentanide phenyl propanone. So these are 3 examples of Nourish type 2 reaction, which are very, very important, and important for the competitive exam. Doesn't need to say it again. So next we will learn about the dipymethane rearrangement. The dipymethane rearrangement is a photochemical reaction of a molecular entity that contains 2 pi systems separated by a saturated carbon atom, that is the sp3 carbon atom, a 1,4 diene, or an allyl substituted aromatic ring. This can be the substrate of choice. In that cases, I will come into that part, and these will eventually form an ene or allyl substituted cyclopropane. So these are the points that need to be associated with the dipymethane rearrangement, and the important one, that the reaction is stereospecific in character. I will come into example where I will show that these reactions can be of stereospecific in nature. And the rearrangement reaction formally amounts to a 1-2 shift of one ene group, and in case of diene, of course, or the aryl group in case of allyl aromatic analog, and the bond formation between the lateral carbons of the non-migrating moiety. So these are the point that need to be understand when we proceed for the dipymethane rearrangement. This is a simplest example of dipymethane rearrangement, as you can see over here, and And first, I would like to say that the rearrangement which originally encountered in the photolysis of, as I said, yes, this one. So this is the photolysis of beryllium to give the semi-bulvalin. So this was the first encountered compound, and the rearrangement was originally encountered in the beginning with that by the mechanism. However, the mechanism was re-established by Zimmermann later on in 1967. So I will talk about that next. So here in the beryllium, you can see this is a biphenyl system. This is a bicyclic system as well. Upon photo irradiation, it goes the C8H8 aliphatic hydrocarbon system. The two possible options are there. Either it can go the direct photo irradiation or photochemical reaction without any sensitizer, and in that case it will eventually lead to the another structural isomer, the C8H8 hydrocarbon system, which is cyclooctatetraene. However, if it goes with the sensitized condition or in presence of sensitizer, it will lead to the semi-bulvalin as the major product. Okay, so these need to be understand that for acyclic system in dipymethane rearrangement, there is no other option but to go for the acyclic system under photo irradiation, having the two pi systems connected with one sp3 carbon, definitively the dipymethane system. This will go to the dipy rearrangement product. However, in case of cyclic system of dipymethane, upon photo irradiation, if it goes the direct photochemical reaction without sensitizer, it will lead up to the structural isomer, and if it goes in presence of the sensitizer like acetone or some other sensitizers, the dipymethane rearrangement product will be the major one. Okay, so these are first thing to understand from that point of view. Second one is the direct photo irradiation, and you can see the product is the phenyl cyclopropane, and the mechanism will involve the process as mentioned over here in this pathway of the general procedure of the reaction. The reaction will process in the similar way. If we go for the next one with the photo irradiation of this cyclopentenone having the other alkyl chain, so eventually these are the dipymethane system. If you go along this way, so this is the dipymethane chain highlighted part, and upon photo irradiation it will yield the cyclopropane ring structure into the final product, and in 66% of yield. Another acyclic system involving heavily substituted phenyl substituted dipymethane system, upon photo irradiation and without sensitizer, this will eventually lead to the cyclopropane ring system again. And in this case, if you substitute this the terminal, one of the olefin terminal of this dipymethane system with methyl group in the cis form, the compound eventually, the cis compound will eventually end up with the cis product. And the trans compound will eventually lead to the trans product, thereby confirming that the reaction or the dipymethane rearrangement is a stereospecific reaction. I hope you understand that point. There are other examples. Here you can see the benzoberylene can have two different mode of actions in presence of photo irradiation. In absence of sensitizer, that is the direct photo irradiation, can lead to the, as I said, the structural isomer benzocyclooctatetraene, and in presence of acetone sensitizer it will lead to the semi-bulvalin derivative, that is bench semi-bulvalin compound. So the direct mode and the sensitized mode yields different products. I hope this is understandable. And in the next example you can see the dihydro the bicyclic system, of course, the dihydronaphthalene dicarbonitrile, and upon in presence of sensitizer acetone and photo irradiation, it will lead to the tetrahydrobenzocyclopropenyl pentanyl pentylene 1,2 dicarbonitrile as the major product in 82% yield. The second reaction of that is also a dihydronaphthalene 2,9 dicarbonitrile. The position of the nitrile group or the cyano group is changed in that substrate, And again, in presence of acetone sensitizer, the photo irradiation gives the product of dihydrobenzocyclopropanil pentylene dicarbonitrile in 90% yield. Okay, so the nitrile group orientations will lead eventually to different products, and these are examples of the dipymethane rearrangement reactions. So I will be showing here another example, which is the substrate is here the cyclobutyl naphthalene monocarbonitrile in presence of dinitrile system. This is the mononitrile system here. So in presence of the sensitizer and photoirradiation, the biradical will be generated, and as you can see, the alpha bond adjacent to the cyano group that ruptured or that broken, and eventually the pi bond is generated here, and the radical at which the cyano group is generated at that position, and that will lead to the formation of the dihydro benzocyclopropanil pentylene the carbonitrile. So monocarbonitrile will eventually lead with the monocarbonitrile in 90% yield. Another example is the benzo fused bicyclic system. So this is the dihydronaphthalene, you can say, in that sense. So if it goes with the photo irradiation in presence of the sensitizer, it will form the dihydrocyclopropyl as the product, and the mechanism you can see over here is as shown, which involves the dipymethane rearrangement reactions. Here the dipymethane system is considered to be that one. Okay, so then after the usual rearrangement reaction, formation of the radicals, as I said, eventually leading to the cyclopropane formation is the basic criteria for this dipymethane rearrangement. So now we will see the example or the application of dipymethane rearrangement in the natural product synthesis. Okay, so in the natural product synthesis, first we will see that from erythrolyte B we will get erythrolyte A by means of photochemical reaction or photoirradiation involving the dipymethane rearrangement reaction, and the yellow dotted circle shows the part of the whole molecule of erythrolyte which is used or which is taking part in the dipymethane rearrangement reaction. Okay, so here the reaction can proceed in two different conditions. The photoirradiation can take place with the quartz vessel. The vessel is made up of quartz, and in presence of benzene as solvent, 87% of conversion can take place in 3 hours. So this is one condition. The another condition can be 5% of methanolic seawater, and the glass in the erythrolyte B will be taken in a glass vessel, and with sunlight 37% of conversion can take place in 8 days, and eventually that will lead to the erythrolyte A as the final product. So the natural product synthesis from erythrolyte B to erythrolyte A is possible by means of dipymethane rearrangement reactions. So there is another reaction here where the bicyclic system you can see in the left hand side as the substrate. Upon photochemical irradiation in presence of acetone sensitizer will eventually go for the dipymethane rearrangement reaction and form the cyclopropane ring, as you can see, which further with another radical reaction in presence of AIBN, which is radical initiator, and tributyl tin chloride in presence of benzene solvent. Eventually that will lead to a 5,5,5 fused the tricyclic ring, the tricyclic carbonyl compound, and from there a natural product named capnylene can be obtained, which is a triquinane sesquiterpene. So this terpenoid capnylene can be obtained by means of dipymethane rearrangement using this rearrangement reaction in one of the steps to obtain the natural product. Next comes the oxidipymethane rearrangement. So with the dipymethane rearrangement, it need to be understand that if there is a heteroatom present in the pi system, then it also undergoes the dipymethane rearrangement reaction in a similar fashion. And if the heteroatom is oxygen, then the rearrangement is known as oxidipymethane rearrangement. I will come with the AJA one also. So in that case, you will see that the nitrogen equivalent of this oxidipymethane rearrangement reactions. This is a simple example of oxidized rearrangement. The only option or the only part that the pi system has now incorporating a heteroatom, which is oxygen. So this is the dipi methane system here. Uh, the dienes are attached or joined by means of a sp3 carbon center, and in presence of photochemical irradiation, the biradical generation proceeds as usual and eventually lead to a cyclopropane ring formation. So one thing need to be understand that in all cases cyclopropane ring formation is the usual expected product, and for this oxidized rearrangement we never obtain the oxidant as the product. Okay, so this is one thing to be remembered. There are several examples falling under this category. Here you can see with this fused 6,6 fused the carbocycle with the carbonyl compound and having the dipymethane structure. It goes in presence of pyrex glass vessels, in presence of tertiary butanol and photochemical irradiation, eventually lead to the formation of a cyclopropane ring here, as you can see in the middle, flanked between the two ring structures. Another example is this one, the bicyclic system having a cyclopropane ring already into the structure, and this dipymethane rearrangement will proceed in presence of sensitizer to produce the cyclopropane fused these bicyclic systems. The carbonyl compounds will be the carbonyl functional group will be intact, and we will get a product according to the previous mechanisms that I have shared with you. In another example, you see this 4,5 fused ring system, which is again a oxidipymethane system, undergoes rearrangement reaction in presence of acetone sensitizer and photoirradiation, give yield to the desired product in 70% of yield. Another example of this bicyclic system in presence of sensitizer and photoirradiation gives the desired product or expected product, rather say. So all these examples are very important and can help you during the competitive exam, where you are preparing for, like it can be the CSIR net or your not usual the traditional undergrad or postgrad chemistry exam papers as well, organic exam papers, definitely. There is one competing factor with the oxidipymethane rearrangement and 1,3 acyl migration. So these are, for example, if you see in the middle the substrate, here the oxidipymethane ring system here, this one is the oxidipymethane ring system, and it can go two different pathways and to follow two product, and with the intermediate, as you can see here, with the biradical system. And if it goes with the 3 nanometer wavelength of irradiation and hexane being the solvent, it will end up with a 7,5 fused ring structure with beta gamma substituted carbonyl compound. However, if in presence of acetone sensitizer the irradiation used of 254 nanometer, this has been optimized, and that will lead to the dipymethane rearrangement reaction and formation of the cyclopropane ring structure. So these are competing factors depending upon the solvents and the sensitizer and also the wavelength of the irradiation, and different products can be formed accordingly. This is another example where this oxidipymethane rearrangement can eventually lead to the formation of a bioactive molecule, pinguisone and deoxypinguisone. So these are very important reactions as well. Eventually, if you don't remember the name, this is also okay, but the reaction that proceed here first, so this need to be memorized, and these are example of this competition or the between the oxidipymethane and 1,3 acyl migration. Next come azadipymethane. As I said, if the heteroatom is nitrogen in a dipymethane system, then that should be termed as azadipymethane rearrangement reaction. And so this is a very easy example or similar example of oxygen kind of. So in that case, you see the photochemical irradiation in presence of sensitizer of this dipymethane system, having nitrogen atom incorporated into the structure, generates the radicals accordingly, and then eventually breakage of the bond and lead to the other two radicals, and therefore the cyclopropane ring structure is generated and an imine structure is formed. So this is the major product in case of aza-dipymethane rearrangement reaction. So you need to understand this rearrangement reaction quite well. So this is another example of aza-dipymethane rearrangement reaction, as you can see. So this is the aza-dipi system, the yellow highlighted one with the acetate, N-acetate as the protected nitrogen in presence of acetophenone as sensitizer, and eventually it lead to the cyclopropane ring formation as expected for the dipymethane rearrangement reaction, and the further reduction will lead to the formation of cyano group from the N-acetate substituent. It forms the cyano group. So we will end up with a 3 fused ring structure bicyclic system with a cyano group and a phenyl group as the substituent. So in another example, if you can see, this is another example of this aza-dipymethane system. So you need to understand or realize the aza-dipymethane moiety or skeleton where the reaction takes place in presence of acetophenone sensitizer. 65% yield of the product is obtained, and you can see here the formation of the cyclopropane ring structure here, and this oxime is formed, so or kept intact. Next comes the 2+2 cycloaddition reaction. In 2+2 cycloaddition reaction, it is the cyclization of two olefinic units to provide a cyclobutane ring structure, and here a generation of two new CC bonds happens, and up to 4 new stereocenters can be generated. And just let me take you to the first example of this 2+2 cycloaddition. As in way back in 1908, the first 2+2 addition was observed when carbon was exposed to sunlight for 1 year and generated thereafter the carbon camphor after photo irradiation in sunlight. So these transformations belong to the classic reactions that generally can be rationalized by the Woodward-Hoffman rules. Okay, and this 2+2 cycloaddition is very important and photochemically allowed, and it provides a practical way to synthesize the cyclobutane derivative. This is very important. The cyclobutane ring structure opening and hexatriene ring closure belong to the most frequently investigated electrocyclic reactions that we encountered during the pericyclic reactions and also in the photochemical reactions as well. So I will show here another example here where the intermolecular 2+2 photocycloaddition takes place in case of this vinylic ether moiety. In presence of the photosensitizer and photoirradiation, it provides two structural isomers, and obviously you can see the cyclobutane ring structure has been generated. So this is the tradition of the 2+2 cycloaddition reaction. Okay, so in photochemical conditions, it creates a charge like umpulong, we know that, and of the enones, where the beta carbon is electron rich. So this facilitates the reaction process, and also the intermolecular variants are known, but those are quite regioselective and can highly be dependent on both the olefinic partners. Okay, and this 2+2 cycloaddition reactions, of course, it follow the rule of 5. Maybe in my next lecture or during the problem solution time, I can talk about that. And none of the other regioisomers was observed, as you can see here in the right hand side, that when the carbon was irradiated, it didn't yield the other regioisomers, as you can see here that it was not observed. So this was quite specific, and the other regioisomers are not forming in this photochemical irradiation or 2+2 cycloaddition reaction. So here are other example where the enone compound, cyclic enone compound, when reacts with alene compound, the simplest alene, under diethyl ether solvent, the photochemical irradiation, of course, again yields the 4,6 fused cyclic structure, and the mixture of structural isomer, as you can see here, in a ratio of 2:1. So those are the cyclobutane ring formed, and of course, because of the alene, we get a exocyclic double bond. Okay, so this is another example of 2+2 cycloaddition reaction in the synthesis. And when this structural isomer or the bicyclic compound under several steps provide the periplanon B compound, which is a kind of total synthesis or short total synthesis, you can say. I have another example here where you can see the starting compound in the left hand side. Also it undergoes the 2+2 cycloaddition reaction here. So the involved pi bonds are this one and this one, highlighted in yellow color here, and when it undergoes at 0 degree centigrade in presence of a mixture of solvent of acetonitrile and acetone, under the photo irradiation, you can see the 2+2 cycloaddition proceeds, and we can have a formation of a cyclobutane ring. So it gives a complex fused cyclic structures with heteroatoms constituting the cycles, and in several steps again it can be used to prepare Saudin as the major product. So these two are the example where 2+2 cycloaddition reaction were used for the synthesis of bioactive compounds. So viewers, if you like my video and the content of the videos, then please subscribe my channel, and don't forget to press the bell icon to get notification whenever I upload the video. It will be notified to you, and it can help you in your exams on other purpose as well. So next I'll be talking about the Dimeyo reaction, and for this one, in Dimeyo reaction, the enol of a 1,3-diketone reacts with an alkene, or in another species with a CC bond. So the double bond needs to be there in the other species also, and the resulting cyclobutane ring undergoes a retroaldol reaction to yield a 1,5-diketone. So this is basically the Dimeyo reaction. So 2 points need to be memorized here. One is the 2+2 cycloaddition involves the double bond of an enol and another olefin, and the retroaldol reaction then after proceeds. Okay, and the ensuing retroaldol cleavage is favored by the relative instability of the cyclobutane ring. So that part is utilized, the instability or the strain whenever the cyclobutane ring is formed, that we know from the Bayer strain theory. So those small sized rings are strained. So that has been utilized here in the Dimeyo reaction. And now if we see first example, that the substrate, as you can see, the enol of 1,3-dicarbonyl system reacts with an olefin having an electron withdrawing ester group. Then the 2+2 cycloaddition reaction proceeds under the photo irradiation to yield the fused bicyclic system, the 6,4 fused bicyclic system, and the cyclobutane ring is formed, which is constrained by means of Bayer strain theory, and therefore that facilitates or that acts as the driving force for this retroaldol reaction eventually end up with a 1,5-dicarbonyl cyclic compound, and the ester moiety is intact here, and which carries over from the substrate. So we will realize that with another example of the Dimeyo reaction, and here the ester the enol ester of this 1,3-dicarbonyl substrate, when reacts with the ethylene 1,2-dichloroethylene under photochemical irradiation, again it eventually forms the cyclobutane ring structure, you can see over here, and upon reaction with potassium hydroxide base, this ester groups cleavage and formation of this oxygen anion. So this oxygen anion undergoes the ring opening, and this ring, the constrained fused ring structure, bicyclic ring structures get opened, and we get eventually a 7-membered ring structure, as you can see here as the intermediate. So this intermediate further goes on releasing a chloride anion and a HCl molecule, and eventually ends up with gamma tropolone as the major product. So these are a couple of reaction of Dimeyer reaction. In some cases we miss the Dimeyer reaction, and this can be important or fruitful in some exam as well. Next, I will talk about the photodimerization reaction. For this purpose, the direct excitation of the alkenes to the first excited state is generally understood to lead or to yield to cycloaddition reactions, right? And from the excited singlet state, of course, that happens from the excited singlet state. And for the triplet sensitized alkenes, that also observe to yield the photodimerization reactions. So here I will be showing 4 examples of photodimerization reactions, and the first one is here with a cyclopentenone upon irradiation with photochemical or photolight or photons, end up with a dimerized product and mixture of structural isomers, as you can see over here, and eventually this 2+2 cycloaddition for this photodimerization ends up with a cyclobutane ring at the junction of the 2 fused 5-membered rings. Okay, so let's come to the second example, where the maleic anhydride in solution phase, when photoirradiated, ends up with the structural isomers, and of course their dimers. This is another example. The third example is from the trans-cinnamic acid. It can undergo the photochemical reaction to produce the alpha-truxylic acid and beta-truxylic acid. These are another example of dimerization reaction. The fourth one is from the Dienone system, the dimethyl substituted Dienone system. This again on pi2 plus pi2 cycloaddition reaction under the photon or the photochemical light, it forms the dimer, and here also you can find the cyclobutane ring in the molecular skeleton. So these are examples of these photochemical reactions, and then I will talk about the photo reduction. And for the photo reduction, I don't know you know or not, but the photo reduction of benzophenone is very important example. And for this photo reduction of benzophenone by the alcohols, it has been very well studied for a long time, and this may lead in high yield to the aldehyde or ketone, which derived from the alcohol, and eventually end up to the benzophenacol, or if we use the alkaline medium, that will end up with the bench hydrol. Okay, so this is the reaction process. Here I will be talking about the diaryl ketone, as you can see here in the first here. So the diaryl ketones do not undergo the photodissociation in the same way as the alkyl ketones. Okay, so probably because the cleavage of to the phenyl and other aryl radicals is unfavorable. However, the aromatic ketones are photochemically reactive, and in presence of the compounds that can donate a hydrogen atom, with the result that the carbonyl group is reduced. Okay, so this is the final concept of the photoreduction of the diaryl ketones. And here one of the classical photochemical example I have picked up here, that with the benzophenone, when reacts with biphenyl alcohol in presence of benzene solvent and the light, end up with benzophenacol as the major product. So as you can see first here with, allow me to take the highlighter. Yes, so the benzophenone first reacts with the diphenyl alcohol in presence of photoirradiation. This is the final product of the benzophenacol. So now we see how the reaction proceeds, and we can see that the light is absorbed by the diphenyl ketone or the diaryl ketone, and it goes to the singlet state, excited singlet state, and then at the excited singlet state, the intersystem crossing can proceed, and it goes to the excited triplet state. Okay, so at the excited triplet state, the activated ketone removes one hydrogen atom from the alcohol. So from the alcohol, it can take a hydrogen atom, and eventually a radical will be generated there. okay, and that will be generated from the benzophenone, and this the final benzophenol will be resulted from the dimerization of this radical. Okay, so this is how benzophenone is get reduced photochemically to benzophenol. So this is an example, or classic example rather say, of the photo reduction of benzophenone. Okay, so next I'll move to a very important reaction which is known as the Paterno-Bucci reaction. The photochemical 2+2 cycloaddition of an alkene and a carbonyl group is known as the Paterno-Bucci reaction. Okay, so here intra and intermolecular examples both are known because this is a well-studied reaction, and in many cases very high diastereoselectivities can also be observed. Okay, and what are the main product of that one? You can see the 2+2 cycloaddition between the carbonyl and olefin will eventually end up forming an oxytane ring structure. Okay, so this is the characteristic or identification pattern of the Paterno-Bucci reaction, looking at the product. So here this is the simplest example you can see with acetone. When photo irradiated, the molecule get excited, and when it reacts with an olefin, it eventually end up with a oxytane ring structure. Okay, so as you can see over here, the oxytane ring structure is the major product of reaction of a carbonyl and an olefin. Okay, so here another example are there with the benzophenone taken as the carbonyl substrate. When photo irradiated, moves to the or transferred to the excited state, excited triplet state to be specific. When it reacts with the olefin, it can end up with two biradicals, right? There are two possibilities. So one can be the 2-degree radical, as you can see here. So this is the 2-degree radical over here. Another one is a 3-degree radical. Okay, so as I said that in photochemical reaction, the stability of radicals is a very important phenomena, and we need to consider that very carefully. So here 3-degree radicals being more stable will end up with the oxytane ring structure, and this will be the major product. Okay, so we can have the oxytane ring structure with from the other radical generated, but that should be the minor product, as the radical which is generated, biradical which is generated initially, is less stable in that case. So I will be talking about showing some more examples on Paterno-Bucci reaction. For example, here you can see that benzophenone molecule, when reacts with the cis and trans olefin under photo irradiation, it can produce the oxytane ring structure, and the mixture of oxytane ring structure cis and trans depending on the cis and trans substrates. Okay, so with another example here with a cyclic system, here you can see the involved olefinic and the pi bond and the carbonyl group are these two, eventually ends up with an oxytane ring structure here, and this upon reaction with hydrogen iodide and acetic acid can form a bicyclic 6,6 fuse structure. Okay, which eventually is a part of the steroidal ring system. Okay, so in those cases also this Paterno-Bucci reaction is applicable or find its way. So then comes the Paterno-Bucci reaction in the synthesis, and here I would like to share with you for the synthesis of endo hirsutene, that compound we want to synthesize that one using the Paterno-Bucci reaction. So let's see how this process goes on. So first, the substrate we receive or get the substrate or obtain the substrate by means of the Diels-Alder reaction, and here also you can recognize the olefin and the carbonyl part which undergo the photochemical irradiation in the Corex glass vessel. So therefore the wavelength for the photo irradiation needs to be more than 250 nanometer, and in benzene solvent when the reaction proceed, you can see this is the oxytane ring structure that has been formed by means of the Paterno-Bucci reaction. So the initial state of this synthesis of endo hirsutene, the Paterno-Bucci reaction has been utilized. Next, it reacts with the oxytane ring need to be opened up, and in that case, the magnesium salt of isopropyl amine, when heated first, followed by pyridinium dichromate, which is also known as the Conforth reagent, and in presence of dimethyl formamide, the oxidant ring opens up. Okay, so again forming the carbonyl and the olefin, but you can see the orientation and the ring structure here has been changed. So then comes the reaction again with this carbonyl and olefin system, when it reacts with LDBB, which is actually the lithium 4,4,4-ditertiary butyl biphenylate. So upon reaction with that compound in THF at a very low temperature, you can see minus 78 degrees centigrade, the 5,5,5 fused, the tricyclic enone structure is obtained. Okay, which on further reduction by means of sodium borohydride and trifluoroacetic acid will end up with the endo hirsutin compound as we intend to synthesize. So this is a representation of a synthesis of a bioactive compound where Paterno-Bucci reaction has been participating or providing as a pivotal role in the synthetic route. Next, I will focus on the furan compound, how it can take part in the Paterno-Bucci reaction, and also the carbonyl part will be taken differently. So here in this slide and the next one, I will be talking about the variation of furan and the carbonyl counterpart in the Paterno-Bucci reaction. So here first you can see that 2,5-dimethyl furan derivative has been taken for the photochemical reaction, and here the benzaldehyde is the another carbonyl counterpart. Upon photoirradiation, the oxytane ring structure is produced as expected. This can have two fates, as you can see. The one can be the photochemical variant for the aldol reaction through the transformation of the photoadduct, and the other one can be the 1,4-dicarbonyl compound, as you can see here as the major product here. So in the two reaction conditions are different, and of course therefore the products are different in those two cases, but these are variation of this Paterno-Bucci reaction where furan and the carbonyl compound, the structure of them has been varied. And here the oxytine ring structure for the retroaldol, the aldol reaction is also remain, but the reduction takes place as we use the hydrogen and alumina and rhodium for the reduction, and then on reaction or the absorption in wet silite will end up with the hydroxycarbonyl compound. Okay, so the beta hydroxycarbonyl compound, you can see this is the beta hydroxycarbonyl compound as the major product in case of aldol, as we know that. Next, another example for the furan carbonyl variant of the Paterno-Bucci reaction. Here in this case you can find that the furan has been substituted at 3 and 4 positions by the methyl groups, and also in here the carbonyl compound has been taken as 3-benzyloxypropanol. When photoirradiated in presence of benzene and diethyl ether, ends up with a bicyclic ring system, and the heterocyclic structures, of course both of them, one having the furan ring, another one is the oxytane ring fused to each other, and this establishes two stereocenter present in the acetyl toxin compound, which is the target compound that can be achieved in several steps. Of course, after this intermediate or from this intermediate, one can access that one, but my intention is to let you know about the involvement of the Paterno-Bucci reaction for the synthesis of these bioactive compounds. Having said all these examples and utility of the Paterno-Bucci reaction in the synthesis and also in the organic chemistry, rather say, I must say that there are a couple of limitations of these Paterno-Bucci reactions as well. The first one is if the olefin which have the allylic hydrogen, that can have the scope to limit the reaction. Okay, so in that case the reaction can be limited because the allylic hydrogen can be easily abstracted and the complex mixture of products will be obtained in that case. So this can be one binding factor of or the limitation of the Paterno-Bucci reaction. Secondly, if we are going to use the ketone and olefin, and both have comparable triplet energy, or ketone have the higher triplet energy to say, then the reaction of dimerization of olefin and the Paterno-Bucci reactions will compete to each other, and the dimerization of olefin will predominate in that case. So we will not get the Paterno-Bucci product in that case as well. Next, I will be talking about a very important reaction, photophrise rearrangement. Okay, the photophrise rearrangement reaction was discovered by Anderson and Rees that involves the homolytic cleavage of a carbon heteroatom bond, and that will be or maybe carbon oxygen, carbon sulfur, carbon nitrogen, and these bonds will be of esters, thioesters, or amides respectively. Okay, the radical mechanism of the photophrise rearrangement is quite well established so far, and it is known that the rearrangement occurs mainly through the excited singlet state. This is very important to memorize. And the previous studies on this product distribution of the photophrise rearrangement reactions shows that in addition to the ortho and para products, the corresponding aryl alcohol, thiol, or aryl amines are also formed in the reaction. So here you can see the aryl ester molecule, which upon photoirradiation undergoes the photochemical rearrangement known as the photophrise rearrangement, and eventually ends up with para-acetyl phenol and orthoacetyl phenol, and of course there will be some side product of phenol as well. Another two reactions where you can see the phenolic ester in the second one, the phenolic ester of alkane sulfonic acid may also undergo this rearrangement reaction to produce the ortho and para product, substituted product, sulfonic acid substituted phenol, and also phenol as the side product. Another one is for the anilide systems in presence of the solvent. The photoirradiation lead to the formation of orthoacetyl and para-acetyl substituted aniline systems, and aniline as the byproduct as well. So photophrise rearrangement are quite important and quite explored so far, and is for the competitive exams, this is also important in that sense as well. So next I'll be talking about the Barton reaction, one of the most important reaction of photochemistry, and sometimes this is also known as the Barton nitrite ester reaction. Okay, so either the Barton reaction or in the name of Barton nitrite ester reaction, because depending on the nature of the substrate. Now this is a photochemical reaction that involves the photolysis of an alkyl nitride, and in the dissociation of the alkyl nitride, eventually it will form a delta nitroso alcohol. Okay, and it was discovered quite back in 1916 by Sir Derek Barton, and for that he eventually got the Nobel Prize as well. And this is the reaction sequence you can see with an example, and here mainly you need to understand that the Barton reaction involves a homolytic, the alkyl oxygen and the NO cleavage. So RO-NO cleavage is there, the homolytic cleavage, and this followed by a delta hydrogen abstraction, then the free radical recombination and tautomerism to form an oxime. Okay, so you can see that the nitroso alcohol this is also an oxime. Okay, and often the site and the selectivity is important for the delta hydrogen is a result for the conformation of the 6-membered radical intermediate that is formed. This gives the abstraction of the delta hydrogen within the molecule, and often the site of hydrogen atom abstraction can easily be predicted or picked up looking at the substrate structure, and this allows the regio and stereoselective introduction of the functionality into the complicated molecules. And due to this unique property, at time to change otherwise inert substrates, also these are extensively used for the synthesis of unnatural steroid analogs. Okay, so that's why Barton reaction is quite important. So if you go with the example here, the nitrite compound will eventually, upon photoirradiation, splits up, forming two radical species, and the oxygen radical species eventually abstract the delta hydrogen, and thereon a recombination of the NO dot, the radical, will end up with another the nitroso product, and this tautomerizes further to form the nitroso alcohol and the oxime compound. And this can have two fates. The oxime can be hydrolyzed to the carbonyl compound. This is one option, as you can see on in the left hand part. This one is this hydrolysis part is of the oxime. This is one option of having the product. And this nitroso alcohol can undergo the dimerization process, and we end up with the nitroso dimer. Okay, so these are two common fates of this nitroso alcohol or the oxime compound, that is the main product of Barton reaction, which eventually undergoes some other reactions as follows. Next, there will be some more reactions, as you can see over here. These are three examples of Barton reactions, and alkyl nitrite again undergo the photoirradiation to produce the nitroso alcohol product, and the other one, the second option, ends up with the same nitroso oxime product. And if you, the first one, the implementation is that if R1 R2 are the alkyl groups and there is no hydrogen there, so eventually the reaction stops over there without further proceeding for the formation of the oxime. Okay, which is possible in the second example. If you can look at the second example, so this hydrogen is for the enolization or the tautomerization to form this oxime part, where here if this R1 and R2 are the alkyl groups, so there is no option, and the nitroso alcohol will be the end product in that case. Similarly here, the reaction can proceed via the similar way. You can have the mechanism is clearly drawn here, so you can have a look, and in the end step, the recombination of the NO dot radical with the carbon radical eventually end up with the nitroso compound, the nitroso alcohol. So these are examples, and now I will be coming to a little bit more complicated. And yes, so this example you can see over here with some steroidal structure here. Now what we need to do, we need to find out the reaction site which eventually generated by reaction of this alcohol with NOCl and pyridine eventually produces the nitrite of the functional group of choice for the Barton reaction, and which then the Barton reaction proceeds. So this one is the Barton reaction step of irradiation, photoirradiation in presence of toluene will end up with the nitroso alcohol compound or derivative, and further the abstraction of hydrogen will lead to the oxime. The oxime will be the OH group of the oxime will be can be protected by acetic anhydride in presence of pyridine to produce the NOAC derivative of the steroidal molecule, and eventually by means of cyclization, by means of sodium nitrite of this the N acetate compound eventually end up with the product like this with the oxygen cycle. So this is some extension of the Barton reaction further to obtain some steroidal analogs. So as I said before, that that is why these reactions are important for. There is another reaction. These are very important because specific type of reaction and substrate and product are there. So this is for the generation of parhydrohistocontoxin. So this is the target molecule, and this can be obtained from this spiral ketone, and eventually after few steps the alcohol comes, and then the reaction with NOCl and pyridine will eventually form the nitrite, the alkyl nitrite compound of the spiroisomer, and then the photochemical irradiation, that is here in the second step we will have the Barton reaction to proceed, and after this nitrite eventually goes up to form the oxime compound, and that upon several steps, but those steps are I didn't put here because those are not very important here, because we are studying the Barton reaction. Eventually that will produce the parhydrohistocontoxin, that natural product molecule. Okay, so these are the reaction regarding the Barton reaction. Next important topic is the arene olefin cycloadditions. Now the cycloadditions between the arenes and the olefin can have three possible mode of additions. Ortho cycloadditions, which is commonly the 2 plus 2 addition, paracycloadditions 4 plus 2 addition, and metacycloadditions 3 plus 2 additions. So I will be talking about these three types of cycloadditions, and I will try to represent by means of examples, and after that we will see a couple of problems regarding photochemistry based on the diazoketones, and basically that will conclude the course of photochemistry. So first, when we talk about the orthocycloaddition, you can see here the arene and the olefin, when reacts with reacts in presence of photoirradiation, they undergoes the orthocycloadditions, and here you can have the R1 and R2 groups written over here in the right hand side, eventually forming the cyclobutene ring structure. So common product, the cyclobutane, as the 2 plus as the major product of 2 plus 2 cycloaddition reaction. So we will see another example here where the benzene reacts with maleic anhydride under the photoirradiation, eventually undergoes the 2 plus 2 cycloaddition reaction again, and producing the cyclobutane ring, which upon reaction with another molecule of maleic anhydride eventually reacts with the 4 plus 2 cycloaddition mode with the remaining intermediate, as you can see over here, and then the two molecules of maleic anhydride get attached with a 6-member cyclic structure, ring structure, having an olefin into that one. So this is the one molecule of that, and this is the another molecule of the maleic anhydride, which is attached with the benzene ring. So these are a couple of examples from the orthocycloadditions. Next, I will be talking about the paracycloaddition, where the reaction with olefin and alene under photochemical irradiation can lead to the paracycloaddition product, that is the 4 plus 2 cycloaddition product. We can have the other polynuclear arene also, and when reacts with the vinyl nitrile under the photochemical irradiation, produce the bridgehead compound having the two phenyl rings flanked attached with this bicyclic system, and substituted cyano group at the position of the bridgehead position. So these are examples of paracycloadditions. Now I will be moving to the metacycloadditions, and this has been a long-standing myth that arenes are photochemically inert, but the Brace-Smith and Blair, they dispelled that long myth, and eventually they were able to find that from benzene under photochemical irradiation it can form fulvene. So this is the structure of fulvene, and this was possible under photochemical irradiation, and this only explains the metacycloaddition reactions. And also another example here you can see with a cis olefin, benzene reacts with the cis olefin under photochemical irradiation, that goes through this biradical intermediate and produce a 5-5 fused ring structure having a cyclopropane ring flanked with that part. So these are example of metacycloadditions, and now I'll be talking about the metacycloaddition in the synthetic application. As you can see here with the substrate, then in order to synthesize the cydrine, the bioactive compound, it undergoes this metacycloaddition reaction as one of the core process, and thereby followed by some other steps with molecular bromine and trialkyl tinhydride, and further with reaction with the hydrazine eventually lead to the cydrine compound formation. So this is an application of metacycloaddition process in the synthetic arena. So next I'll be talking about the first problem, and this includes the reaction of diazoketone benzo-fused triazoketone, of course. And when this reacts with the alkyne substituted with triisopropyl silyloxy group in either side, one side, and another part of the alkyne is substituted with the isopropyl group, and under photochemical irradiation using the Vicor glass vessel and dichloroethane. And then first the reaction proceeds at room temperature, and then further temperature is increased to 80 degrees centigrade, eventually lead to the dihydrophenylene compound. So how that can proceed the reaction, so we will look for that way. Okay, so and here it said that the either substrate can be used to generate the product, and both give essentially the same product of the tricycle, which is eventually the dihydrophenylene. Okay, so let's see how the reaction can proceed. So first you can see here that both the benzo-fused diazoketone will upon elimination of the nitrogen molecule eventually form the carbene. So these are the very traditional way of reaction of the diazoketones. They are very, very important, as they easily eliminates or removes the nitrogen molecule, eventually yielding the carbene. And this carbene can undergo for both the substrate. You see in the third bracket it given the carbene generated from both the substrates, and eventually they will undergo the Wolff rearrangement to produce the ketene, the single ketene from both the carbene isomer. Okay, so this is the tricky part of that eventually you can see with the arrow it's given here how the carbene will be generated. So and then after the reaction with the ketene, the ketene will react with the alkyne part in a 2+2 cycloaddition reaction to form a spirocyclobutanone ring structure with the substitution still on with the isopropyl silyloxy group. And then the 4-pi electrocyclic ring opening will take place eventually to form a modified ketene, and which sets the platform for further 6-pi electrocyclic ring closure via the tautomerization, and eventually that will lead to the dihydrophenylene compound as the major product or our target compound. Okay, so I think the Wolff rearrangement here is the tricky part to have this identify the ketene formation, and then the rest of the reaction involves the photochemical processes to produce the final compound. Okay, so next I will be moving to the next problem. Here the substrate you can see here is the N-allyl oxobutynyl carbamate, the substrate, and there are three conditions imposed on that. First the photo irradiation, followed by ethanol and reflux, and then after the reaction with the pyridine paratoluene sulfonate, with that in presence of that catalyst and ethanol in 2 steps eventually end up with a bicyclic carbamate having a carbonyl compound. Okay, so how this reaction can proceed, so we will see that in the solution. So first the photochemical irradiation on the substrate carbamate will lead the orientation or the cyclization to give the product. Here you can see the ring structure, the formation of the ring structure, bicyclic ring structure from here with an acyclic system. And then the important 2 steps by means of ethanol and reflux will be basically the retromanic reaction for providing this cyclic pyrrole compound, the dihydropyrrole compound having a substitution at the 3 position, and then the manic reaction will facilitate in presence of the pyridinium paratoluene sulfonate catalyst, and then we will get the target bicyclic compound, the N-carbamate with a carbonyl compound. So here the retromanic reaction proceeds first and followed by the manic reaction. So these are 2 key steps to find the solution for this problem. So I would like to tell you viewers that in case you have any queries, whenever it is generated in your mind, you can please type your query into the comment box, and I will be happy to answer those questions or queries in my next class, when I will be talking about the more problems and solutions for which is important for the IIT JAM and CSR NET or GATE exams. So there I will be addressing your queries. Okay, so thank you very much for watching the TG Chemistry, and please subscribe my channel if you like, and press the bell icon as well, and I will be bringing such new videos on the topic of chemistry, different aspect of organic chemistry, in forms of the lecture, full course lecture as you see for the photochemistry, and then I will be bringing some more videos on the photochemistry, like the multiple choice questions on photochemistry and the problem and solutions for the photochemistry as well. So thank you very much.